This is lecture 23 and we are continuing our discussion on 1D premixed laminar flame propagation. And in the last class we had derived the energy equation for our situation. It has a set of assumptions. I hope you remember all of these, and towards the end we assumed Lewis number equal to 1, and after doing all that we got a simple version of the 1D energy equation for steady flow. And before we closed yesterday, we wrote an expression for the right hand side of this energy equation, which I had shown yesterday to be equal to minus m dot f triple prime into delta H c. So, delta H c is the heat of combustion. So, if you look at this expression, delta H c has been written to be the same as enthalpy of formation of the fuel plus nu times enthalpy of formation of the oxidizer minus 1 plus nu times enthalpy of formation of the products. So, this can be identified as the heat of combustion, because this part is the enthalpy of the reactants. Under what conditions? Standard conditions. So, 1 atmosphere 298 Kelvin. That is why we are writing this 0 on the top. So, that means this is the enthalpy of the reactants if they are entering our control volume at 1 atmosphere and 298 Kelvin. Otherwise, we would have written something else. Otherwise, there would have been a term like Cp times delta T for the fuel, then another Cp times delta T for the oxidizer. So, those are not there. So, that means this is enthalpy of the reactants at 1 atmosphere 298 Kelvin. Similarly, for the products. So, the only thing which might confuse you is why do we have nu here and why do we have 1 plus nu here? That is because of the chemical model that we assumed. We assumed that 1 kg of fuel reacts with nu kg of oxidizer to give 1 plus nu kg of the combustion products. So, that is why we have 1 plus nu here. So, this is enthalpy of the reactants minus enthalpy of the products. So, that gives you this delta H c. Based on that, going back to this energy equation, we can write this. So, this is our energy equation. This is something with which we are going to work further. Now, in order to proceed further, we can actually try and say something about the temperature profile. Now, in our approach, in the approach that has been followed by turns, temperature profile has not been solved for, but rather he has assumed a temperature profile. So, we will assume a temperature profile and use that temperature profile in this energy equation. Now, what do we mean by a temperature profile? So, let us look at this. If this is the flame zone, then the temperature can be approximated as T equal to T b here and T equal to T u here. Okay. So, this is this zone of some thickness delta over which temperature will change from T u to T b. We can say that first within the unburnt region primarily temperature is T u, and within the burnt region primarily temperature is T b. So, it is very close to temperature T b, this is very close to temperature T u. Okay. The problem of course is in this region. This is the flame region. So, the flame region, in the flame region there will be preheat zone and there will also be a reaction zone. Okay. That we know from the basic understanding of the structure of a flame. Now, what turns are done is to assume that this variation from T u to T b is linear. So, this is linear. So, this is T as a function of x and this happens to be linear, and he has placed x coordinate from here. So, this is x equal to 0. Now, why is it linear? It is actually not linear, of course. If it is linear, then you can see that this is there is a sharp change here, there is a sharp change here, but this is again for the sake of simplicity. In reality, you will get a more rounded kind of temperature profile here, especially at the edges, you will get more rounded profile, but this is not a bad assumption. And with this assumption of temperature profile, we will try to integrate the energy equation. So, the energy equation is again this one is the energy equation. So, we are going to use this with this sort of a temperature profile. Now, this is similar to boundary layer solutions using integral methods in fluid mechanics, where a velocity profile is actually assumed and then the equations are integrated. Okay. So, this approach is something similar to that. So, here also we will integrate. Now, before we integrate, let me write the boundary conditions also. Temperature as x goes to minus infinity is T u, temperature dt dx when x goes to minus infinity is 0, then so you get things like this. So, far into the unbound region there is no temperature gradient. So, dt dx goes to 0, temperature is uniformly T u, and far into the burnt region also there is definitely no temperature gradient. Okay. So, dt dx as x tends to plus infinity is also 0. So, we will keep this picture in mind. You can copy it on your notebook also, and then first integrate the energy equation that we had on the last slide. We will integrate this between minus infinity and plus infinity. So, we will get something like this. The energy equation the energy equation was like this. So, first let us write it in a slightly more convenient form. And we will divide by Cp, so that it becomes m dot double prime so it is this one now, and we will integrate this. So, let me keep the equation here and keep the figure in mind. We will now integrate from minus infinity to plus infinity. So, on integration you should get this is after integration. So, dt dx as plus infinity, dt dx at minus infinity, both are 0. Okay. Both are 0. So, m dot double prime this So, this is okay, this is a form of the energy equation, but we will also like to write it in a slightly different form using dt dx. Now, dt dx is Tb minus Tu by delta. dt dx is 0 everywhere except in the flame thickness zone, isn't it? We had this, and this is delta, this is Tu, this is Tb. So, dt dx is Tb minus Tu by delta, and using that what I will do is I will replace this dx in terms of dt.
Why this mid-term become 0, sir, in first equation?
This term, the second term, okay, this term becomes 0 because this is dt dx at dt dx is plus infinity, this term is minus k by Cp times dt dx is plus infinity minus dt dx is minus infinity, okay, and dt dx is plus infinity is 0, dt dx at minus infinity is also 0. So, we get this, and let me just write mainly focus on, let me just focus mainly on the right hand side term, left hand side term is okay. So, the RHS is minus delta Hc by Cp, and here we had m dot f triple prime, dx is delta divided by Tb minus Tu into dt, okay, and this is now integration in temperature. This integration now is in temperature. Dx was between minus x was between minus infinity to plus infinity. We were integrating across the domain, right. This is how, this is where x started from. So, what will be the limits on this one? So, it will be Tu to Tb, Tu to Tb, Tu to Tb, that is the right hand side, and we define an average reaction rate m dot f triple prime bar as m dot f triple prime dt minus Tu. We are just calling it the average reaction rate. So, it is m dot f triple prime integrate with respect to temperature between Tu and Tb. That means the entire domain, and we are dividing it by Tb minus Tu. So, that is the temperature variation. So, over the temperature range, how much the reaction rate has changed. So, integration of that reaction rate. So, this is the total integrated reaction rate, dividing it by the temperature difference. We are calling it an average reaction rate. So, if you do that, then yes. So, we have this as an average reaction rate, which is m dot f triple prime bar. So, we are just defining it. We are this term, this part, we are giving it a name. We are calling it an average reaction rate. Now, if you look at the expression, the numerator has the reaction rate integrated over the domain. Okay. and the denominator has the temperature change across the domain. So, we are calling it this ratio, we are calling it an average reaction rate. Now, why are we integrating m dot f triple prime with respect to temperature? Just think about what we learnt in chemical kinetics. M dot f triple prime, of course, is the reaction rate, isn't it? Mass rate of, it is the mass rate of production of the fuel, correct? And this is per unit time, per unit volume, per unit time, per unit volume. What is the rate of production of fuel mass? That is m dot f triple prime. Now, physically, it is easier to write it in terms of temperature than in terms of x. Okay. Does that make sense? Where will m dot f triple prime come from? It will come from a chemical kinetics model. It will have to come from a chemical kinetics model, which will have this pre-exponential factor, it will have concentrations, it will also have that energy factor which has a temperature in it, okay, exponential minus E over R bar T. So, we fundamentally know that the reaction rate can be written in terms of temperature. Okay. So, that is why we are integrating with respect to temperature, dividing it by the total temperature change and giving it a name, we are calling it an average reaction rate. So, that is m dot f triple prime. This is just a shorthand, this will just help us write the equation more conveniently. So, we will go coming back to this. This is the energy equation that we are working with, and the right hand side we wrote in terms of this and that is equal to minus delta H c by C b. We can take the delta out, then we will get m dot f triple prime integrated divided by T b minus T u. So, that is m dot f triple prime bar, correct. That is the right hand side. That is the right hand side. The left hand side is m dot double prime into T b minus T u. So, our energy equation is now m dot double prime T b minus T u equal to minus delta H c delta C p m dot f triple prime bar. So, this is one form of the energy equation. This is after integration. How have we got this? We had the energy equation from the beginning of this class and integrated this over the domain to get this. How are we going to utilize this? Let us think about this one. We will know T b and T u, correct. T u is the unbound gas temperature. So, that depends on which mixture you have taken and at what temperature. So, you know T u. So, if you have taken, let us say, propane air mixture at 400 Kelvin temperature, then T u is at 400 Kelvin. Or if you say that your propane air mixture is at room temperature, then T u is equal to 300 Kelvin, right. So, T u is known. What can be T b? T b can be the adiabatic flame temperature. T b is the burnt gas temperature, isn't it? T b is the burnt gas temperature. So, if we neglect heat losses from burnt gases, then T b is equal to T u, or T b is equal to T adiabatic, okay, approximately. So, we have good idea about T b and T u. What about delta H c? Delta H c is the heat of combustion. So, depending on which fuel you have taken, delta H c, which is the standard state heat of combustion, will be known to you, correct. C p is a value, is a number, and you have already assumed that the C p's of individual species are all equal and they are not temperature dependent. So, we can, if you go to the back of the book, we will be able to calculate C p. What about m dot f triple prime bar? M dot f triple prime bar is sort of an average reaction rate. So, if we have a chemical model, we know that m dot f triple prime, we will have an expression for m dot f triple prime, then we can integrate this divided by T b minus T u. T b is known, T u is known. So, we will be able to say something about m dot f triple prime. Now, what is it that we still do not know in this equation? This is again integrated form of the energy equation. Okay, integrated form of the energy equation, which we can utilize to find things of interest to us. Remind yourselves, what are the things that are of interest to us? We wanted to know primarily which quantity? SL. So, we are looking at the laminar burning velocity. Okay. So, where is SL in this expression? It is in m dot double prime. So, m dot double prime is rho u into SL. So, it is hidden here. So, that is one quantity of interest. But it so happens that getting SL directly from this expression is not possible because of another complication. That is, we still have this delta, and there is no advanced knowledge about delta. We do not know what the flame thickness is going to be like. Okay. So, again looking at this picture, we said that there is some delta. This is T u, this is T b, x starts from here, written all that, but we have not said much about delta. I just said that maybe T b is okay, T u is definitely okay, because you know the unburnt temperature, but we do not know what is delta. So, what is delta? If we knew delta, then we could have used this expression to get an expression for SL, correct, but we do not know delta. So, m dot double prime and delta are actually two things which we have to be able to calculate using this theory that we are developing, and these are in fact eigenvalues of the problem. So, these are two eigenvalues of this problem. So, we need m dot double prime, or if you do not want to talk in terms of m dot double prime, you say SL, and the other thing is delta. So, SL and delta are two things which you are interested in, or in other words, you say that you are interested in m dot double prime and delta. Some people say m dot double prime and delta, some people say SL and delta. So, we need two things, but we got one equation. So, we have to think of using some other equation, and that will also come from the same energy equation. We will play a little trick to get another equation connecting m dot double prime and delta, starting again from the same energy equation. Okay. So, again start with the same energy equation, but get another connecting expression for m dot double prime and delta. So, there we will use this notion that we know something about the reaction rate. The reaction rate is likely to be more important towards the high temperature side. Okay. So, by reaction rate I mean, okay, there is reaction happening between fuel and oxidizer. So, there is a reaction rate which can be thought of as dependent on temperature, or maybe if you want to imagine it in terms of the spatial coordinate, the reaction rate will vary with x. Again, have the same picture in mind, it is going from T u to T b. So, we just schematically had shown temperature as a function of x, but we can also think of the reaction rate as a function of x. So, it will have some variation. What do we expect? Do we expect the reaction rate to be high, closer to the unburnt temperature side, or closer to the burnt temperature side? What do we expect? Burnt side. It will be closer to burnt side, because we know that reaction rate is strongly dependent on temperature, because it has this exponential dependence on temperature. So, most of the reaction is likely to happen within the flame thickness, but closer to the high temperature region. So, again going back to the picture that we are trying to keep in our mind, this is the flame thickness and this is T u, this is Tb. We expect that the reaction rate will probably be something like this. Okay. So, it will get triggered to high values somewhere over here. Some temperature like this, at some temperature like this, the reaction rate will be high. Okay. Before that, the reaction rate is somewhat low. We have seen this before, isn't it? When we are doing Maillard and Le Chatelier's theory also, we defined an ignition temperature. So, there is a temperature which we called an ignition temperature, which we did not know accurately, but which was high enough so that the reaction rate could get triggered to high values. So, this is a temperature at which the reaction rate in fact shoots up, correct. So, this is the reaction. So, we can say that likely, now this is delta by 2, likely the peak reaction rate, most of the reaction will be happening between delta by 2 and delta, correct. Most of the reaction is likely to happen between delta by 2 and delta. So, we will keep this in mind and then again integrate the same equation that we had, same energy equation that we had. So, the energy equation which we were talking about is m dot double prime dt dx minus k by Cp that is the energy equation. Now, we will integrate between x minus infinity and 0. Not 0 to delta by 2, this is not 0 actually, this is delta by 2, this is x equal to delta by 2. So, we will integrate between x minus infinity, x starts from here, x minus infinity is this side, x minus infinity is far into the unbound zone. So, from minus infinity we will integrate to x equal to delta by 2. Why are we doing this? Because we are trying to actually avoid the reaction zone in this integration, okay? Because the reaction zone is after delta by 2, after delta by 2 reaction zone is more important. So, if you do that, we are integrating this energy equation, then we will get something like this. So, is this okay? If you integrate this equation, the first term will give you on integration dt dx will give you temperature, okay. So, what is the temperature at x equal to delta by 2? So, after integration it will become m dot double prime into temperature at delta by 2 minus temperature at minus infinity, correct. What is temperature at delta by 2? Temperature at delta by 2 is Tb plus Tu by 2, okay. So, Tb plus Tu by 2 minus Tu, that is why we got this, correct. And the second term minus k by Cp d2t dx2 on integration gives you dt dx, and that dt dx at delta by 2 minus dt dx at minus infinity, that will give you Tb minus Tu by delta. dt dx at delta by 2 is Tb minus Tu by delta. Okay, so we got all this, and the right hand side will actually be equal to 0. Is that okay? Is it okay to say that the right hand side is 0? Approximately, because we have this integration between Tu to Tu plus Tb plus Tu by 2, that is from somewhere here to the mid plane. So, in this region there is not much reaction happening, So, this integration will give you a very small number close to 0. So, we write this as 0. That was the argument. The physical argument was that in this zone that I marked with red, there is not much reaction taking place. From minus infinity to the mid thickness of the flame, there is not much chemical reaction taking place. That is why I am being able to write this as 0. And you can see that if this is 0, then it actually gives you something very simple. It gives you m dot double prime delta by 2 minus k by Cp equal to 0. So, this is your equation 2 connecting, this is the second equation which is connecting m dot double prime and delta. We had another equation some time back from the full integration from minus infinity to plus infinity. We have integrated the energy equation twice. This last one was between minus infinity and delta by 2. Previously, we had integrated from minus infinity to plus infinity. Okay, minus infinity to plus infinity.
How would is this assumption that the mid plane that you take in delta by 2 to separate the more reaction zone and the less reaction zone?
Yeah, so if your question is that why exactly the mid plane, the point is that mid plane is kind of safe, because we know that much of the reaction will take place close to Tb. That does not mean that there is no reaction taking place. If you look at this carefully, I had drawn some reaction taking place in this region also. So, this will have some effect, but we are neglecting it. Of course, if instead of the mid plane, if you took it somewhere more towards Tu, it would have been even better, but there is no need to be that conservative, because we know that reaction rate will definitely shoot up in the second half. Okay. Again, think about all that physical argument that we had done some time back. 300 Kelvin you get a reaction rate. For a typical activation energy, we saw that if it becomes 310 Kelvin, the reaction rate almost doubles. Okay. So, much of the reaction will take place in the high temperature zone, that is why we are neglecting it. So, this is number 2, and let me, for your convenience, write number 1 also. This you already have with you. So, this was the other equation. So, these are integrated forms of energy equation, right. Fortunately for us, now they look much better, they do not look very complicated, and we can solve this. If we solve this, we will get delta, and we will also get m dot double prime, and we will have m dot double prime after solving 1 and 2. M dot double prime comes out to be this. And there is a delta also. Delta is that is from equation 2 directly. So, that is delta. Let us see. So, we are very close to what we wanted to have. We wanted to have expressions for m dot double prime and also for thickness. You have to get thickness, otherwise you cannot get m dot double prime directly. There is one more little thing that we can do. It is actually possible to write delta H c in terms of T b and T u. So, we will do that also. Delta H c is, as we know, delta H c is this much, and for an adiabatic flame, that is, we are neglecting heat losses from the flame. So, this is delta H c that we already have. Okay. Now, I am writing an energy balance for an adiabatic flame, where the reactants are at 1 atmosphere 298 Kelvin. Then we should be able to write this. Is this correct? This is correct, provided the reactants are at 1 atmosphere 298 Kelvin. Okay. What is the left hand side? Enthalpy of the reactants, provided we are making in this we have made the assumption that they are at the standard conditions, fine. And what is the right hand side? It is nu plus 1 into what is this within square brackets? So, this is at T b, at temperature T b, this is the enthalpy of the products. Okay.
Apart from complete combustion assumption, we are also assuming then stoichiometric combustion, no excess oxidizer.
We are assuming that the fuel is getting completely consumed.
Yeah, but if there is excess oxidizer, then on the right hand side, the enthalpy will also.
Yeah. So, his question is, do we have oxidizer in the products? Actually, there can be, but whatever is coming out, we are just calling it products. Okay. So, we are saying that you have fuel which reacts with oxidizer to give you products, whether the product itself is consisting of oxidizer or not, in addition to the typical combustion products. Okay. That distinction we are not making. So, if you have propane burning with air, if you are giving it a lot of air is the oxidizer, then some amount of oxygen is also coming out with the products, but we are just saying that we have products, that is all, nothing else. So, if it is an adiabatic flame, then we can do this sort of a balance, and based on that we can take this part on the left hand side and write a delta H c, because this is what your delta H c is. Then delta H c will become nu plus 1 C p T b minus T u, correct. So, we have already had expressions for m dot double prime and delta, correct, m dot double prime and delta. Now, in this m dot double prime, we just use delta H c expression that we just now got an expression for delta H c, we are just going to use that. So, yeah, so this is the expression that we have for m dot double prime, and now m dot double prime can be written as this is minus and this is also m dot double prime is also rho u into S L. That means you should be able to write an expression for S L, correct. Here T b minus T u will get cancelled, and if you want an expression for S L, you just divide both sides by rho u. So, that is a slight bit of work, and that is this much, or S L is so that is S L. For delta we had this, and if you write m dot double prime as rho u c rho u into S L, then this can be shown as 2 alpha by S L. It is not hard to go through these expressions and verify for yourself. So, in case you are not sure about a step, just spend some time at home. Ultimately, this is our objective. The objective has been met. So, we have an S L expression, we have a delta expression. We have done plenty of derivation. Now, just let us just think about whether the S L expression seems reasonable or not from what we already know. Now, first of all, it is an equality, but it also has a square root. So, is the square root familiar to us? Did we get a square root in S L some time back? Yes, we did, because the very old theory of Mallard and Le Chatelier that gave S L as proportional to square root of alpha into reaction rate. We had done that, and that took 3 or 4 steps, maybe 5 steps, very easy. So, that was something useful. Now, this actually tells us something very similar. So, it has alpha, it has square root, within the square root it has got alpha, as Mallard and Le Chatelier gave. It also has a reaction rate, isn't it? Because that n dot f triple prime bar is an average reaction rate. So, Mallard and Le Chatelier said that SL is proportional to square root of alpha into reaction rate. This confirms the same thing. So, this is a more detailed theory than Mallard and Le Chatelier, but this tells you that this is proportional to square root of alpha into reaction rate. So, that is good, plus in addition this is an equality. So, that means if we know alpha, if we know the value of nu, nu is, remember, it is mass of oxidizer per unit mass of fuel. So, this is just something which you can easily calculate. You will of course know rho u, which is the unburnt gas density, and you can calculate m dot f triple prime bar based on a chemical kinetics model that you assume. So, if you do all that, then we should be able to calculate a value for SL for the mixture that you have. Okay. So, that is good news. That means we have made some progress. This will be helpful for us in our calculations. Now, delta is the other expression that we got. Delta is 2 alpha by SL. This we did not get from Mallard and Le Chatelier, because there is no discussion on flame thickness in there, but this is 2 alpha by SL. So, that means if you have calculated SL, then you can get the thickness also. So, that is good. Now, let us just spend one more minute on this one. SL has a square root, but it also has a negative sign inside it. So, what does the negative sign mean? M dot f triple prime bar is the production rate of the fuel, an average production rate of the fuel, but fuel of course does not get produced, fuel is getting consumed because of the combustion reaction. So, m dot f triple prime bar is inherently negative. So, the other negative sign which you see in the expression will make the quantity inside the square root positive. So, this negative sign is not spurious, it is actually needed. Okay, you did not make a mistake, I did not make a mistake to get the negative sign, the negative sign very much belongs there. So, that is SL. And we also understand that delta is inversely proportional to SL. If you look at this, 2 alpha by SL inversely proportional to SL. So, higher the laminar burning velocity, smaller is the thickness of the flame. Okay. Now, does this seem reasonable?
Yes, sir. The resonance time should be of the same order.
Yeah. So, if SL has a high value, that means the reaction must be happening fast. Okay, things are happening quickly, a higher value of SL. So, you can think of two situations, one where you have a slowly burning mixture, so SL value is smaller, and in another case you have a mixture which is burning faster, so SL value is larger. If SL value is larger, it typically means that the reaction is getting completed faster, reaction rate is faster. We can see that from the expression also. SL is of course directly proportional to the square root of the reaction rate. So, higher reaction rate means higher laminar burning velocity. So, higher laminar burning velocity means reaction is fast and it is getting completed quickly. If it gets completed quickly, the flame thickness should be small, the zone over which chemical reaction takes place, that is the flame zone, that should be thinner. Okay. So, if you use that kind of argument, then we will be comfortable with what we have got. We got delta equal to 2 alpha by SL. So, that will make good sense to us. Now, we today I unfortunately do not have a lot of time, but I think maybe there is just sufficient time to tell you a little bit about the chemical model, because the chemical model is something which we still have not discussed. See, if you look at the SL expression, we know that we can calculate alpha, we can get nu, nu is very easy, we have the density of the mixture rho u. So, m dot f triple prime bar appears to be the most difficult thing in the expression that we have got. Okay. I have so far just told you that to get m dot f triple prime bar, you need a chemical kinetics model, that is all I told you. But in the next 3 or 4 minutes, maybe I will just tell you how this can be obtained. Yeah.
We have not energy equation.
Okay, if I understand you correctly, you were saying that we had 3 conservation equations, but we used only the energy equation. Is that what you were saying?
Yeah.
Yeah. So, did we use only the energy equation, or we use something else also? Think about this. Actually, somewhere in the process of deriving the energy conservation equation, we used ddx of m dot I double prime as m dot I triple prime. We must have used that, isn't it? If we didn't use this, then we would not have got an energy equation with an m dot I triple prime. Okay. So, this energy equation has already got the species equation embedded in it. So, the species conservation equation for the ith species is ddx of m dot I double prime equal to m dot I triple prime. We have derived that. So, this has been built into the energy conservation equation. Okay. Has the mass conservation equation been also used in the energy conservation equation? Yes, because we have tacitly assumed that m dot double prime is constant, and that is your mass conservation equation. So, it actually has all 3. In fact, there is a momentum conservation equation also. I did not spend time on this, but momentum conservation equation will give you pressure equal to constant basically. For the low speed disturbances that we have, we are talking about deflagrations, and that momentum conservation equation will actually give you pressure equal to constant, right. So, that is also implicitly taken care of. So, all conservation equations have been implicitly taken care of.
So for species conservation, do you mean that ddx of m dot double prime m dot equals to m dot triple prime, so that is again equals to that some expression. So that will be implicitly used to determine the triple prime thing. Is it like that?
Yeah, m dot I for, see, ultimately the first question that you had is whether we are using energy conservation equation only, or whether you are using other conservation equations. So, now what I have answered is that the energy conservation equation has this m dot f triple prime. That means somewhere in the derivation of this energy equation, we use the species conservation equation. The species conservation equation is built into it, right.
But it has some form like involving the mass frictions of fuel
concentrations. Yeah, see, that is the chemical model part of it. So, I was going to go into that. So, in the conservation equation that you see here within this red box, there is an m dot f triple prime, but all that I have said is that we will need a chemical model for this. But I have actually not written an expression for this so far. Of course, the m dot f triple prime will depend on the fuel concentration, it will depend on the oxidizer concentrations that you have locally at any x, and it also depend on the local temperature. Okay, so that is the next part that we have to do, because today we have been able to get expression for SL, but this expression is of value only when we say something about m dot f triple prime bar. That means, when we explicitly say what is m dot f triple prime bar in terms of temperatures and things like that, only then we will be able to calculate it. So, we have not done that so far. So far it is still that okay, SL depends on square root of reaction rate, but to be able to calculate SL, we still need to do more. We still need to be able to write an explicit expression for m dot f triple prime bar. Okay, I think we kind of ran out of time because I was answering this question. So, what I will advise you to do is go through example 8.2 of the book. Go through example 8.2 of the book. This is in the 3rd edition book, this is on page 271. So, this will tell you how a chemical model is used. In any case, we will be discussing this briefly in the next lecture. Any other question? Okay. All right. So, we will close here. Thank you.